All right, let's see what we got going on. How's everybody today? Good. All right. Good to hear it. Well, we have our last focus activity today. If you want to turn those in at the end of class, that is perfectly fine. We'll just wait to the end to do so. But oh, I know. I just haven't clicked it yet. There you go. Yeah, that's okay. But that is absolutely right. It was not the correct focus activity. I just opened that up. But we will talk about that in just a second. These focus activities are going to be the last grade of the 6 weeks. I'm going to record it as a quiz grade. So if you don't turn them in today, please make sure to have them with you tomorrow. There should be extra copies over there in the files by Christian on top of the Chrome card. If anybody has lost or misplaced one, should be plenty of extra copies. Let's see, what else? The main item, other than continuing with our vector lesson today, on Thursday we are taking the district assessment, so it shouldn't take very long. Unfortunately, I was looking over this yesterday, and it looks like it's another test where the majority of the material is concepts that we have not talked about yet. So we'll just try to do the best we can. It's one of those that home office has asked that we go ahead and do it. Lexi? Thursday through Monday, okay. So I'm not worried about the district assessment. If you're not here, I'm not going to worry about it. If you're here, we'll go ahead and take it. I'm sorry? On Friday, hopefully we'll be working on the homework for the vectors lesson we're on. It depends on how far we get today and tomorrow. That'll go into the next 6 weeks, yes. Okay. Brandon. On what? The homework? Oh, the district assessment? Yeah, I mean, it's not for a grade. I mean, if you would like to, I mean, the only thing I'm concerned about is you haven't seen it. How many people are familiar with conics? Parabolas, hyperbolas, ellipses. Oh, she walks to the door. What? That's going to be something we're talking about later. That's the material on the district assessment. But I'm not thinking it's going to take us a whole lot of time. In fact, we'll probably have time to continue on Thursday because, you'll just make the best choice you can. I hate to say it, make your best guess if you don't know the material. It's not counting as a grade. Don't sweat it. It's just one of those things we have to go ahead and do. And I'm asked to compile the data and take a look at what we have, but the data is going to be kind of useless because we haven't talked about that concept yet. But anyways, we will get to it just to kind of give you a heads up. That's what's going to be happening. And then, of course, next week, I did get the email a little while ago. We have the English EOC tests coming up Tuesday and Thursday of next week, the 9th and the 11th. So if you have already passed those, if you don't have to take the test, you've got a late start day on Tuesday and Thursday. The tardy bell rings at 1:35. Okay, so by 1:35 is when you need to be in class. On Tuesday, you're going to see periods 1 through 4, so I will not see you Tuesday. And then Thursday, you'll be seeing periods 5 through 8. I think, yes, you'll probably go to the cafeteria. There'll probably be some kind of area where they'll go ahead and send you. Yeah, because the periods are only going to be 30 minutes on those days, so definitely not enough time to get over to the ATC. But any questions about what's going to be happening? The only other thing I need to mention, we have less than 2 days. Thursday morning by 8:05, I can't stress this enough, if you have any outstanding homework assignments, if there's a retake that you may need to take care of, all of that needs to be done by Thursday morning, because after that I'm going to start finalizing the grades. Okay, so if you need help, come on, let me know. I'll help you out. Okay, so let's see here. This is the correct focus activity. So number 1, it says find the area of quadrilateral ABCD. Okay, so what I would probably do is go ahead and find the area of the 2 individual triangles and then just go ahead and add them up. In fact, it's been quite a while since we saw this. Does anybody remember a little formula that we used to find the area of an oblique triangle? Remember, a triangle that does not have a 90-degree angle if we have a side angle side situation. Doesn't use cosine. He uses sine. What's that, Genevieve?
You need like a side and equal.
Now, you don't necessarily need the law of sines, but you will be using the sine function. The formula, maybe you'll remember it when we see it. You take half Okay, the product of, let's say, B times C times the sine of angle A. So it depends on what angle you're given. Like here, you'll notice I have angle A, which is 110. So if I want to know the area of this triangle ABD, well, I can just apply the formula that I know. That would be 1/2 7 times 11 times the sine of 110. Now, if I go ahead and simplify that, we're going to have the area of that one triangle. Now, I can do the same thing for the other triangle, BCD, but I'm missing something. See, I have a side angle. Oh, that was weird. I don't have that other side. There we go. So I would need to go ahead and figure out what DB is. Well, let's see. Using a law of sines or a law of cosines, is there any way I could do that? Okay, law of cosines. All right, so let's say that this little side right here, DB, this diagonal I'm looking for, let's call that side A because it's directly across from angle A. Okay, because we're talking about that particular triangle. Well, if I'm looking for the length of A, how would I write out the equation? What would start it? Okay, so Brandon says little a squared. So he's absolutely right. What he's saying is b squared plus c squared. So you're saying we take the other two sides, we square them, and then we add them. Okay, so right now we've got 7 and 11. So I'm going to say 7 squared plus 11 squared. And then you said minus what? 2 times those two sides. So 7 times 11. And
then sine big A, right?
Oh. Remember, this is the law of cosine. So this would be the cosine of angle A, but we actually know that it's 110 degrees. Okay. Now this one is very nice. We're not looking for the angle measure. We're just looking for that side length, dB, that we're just calling this little a, right? Well, I don't have to manipulate the equation. In fact, all I have to do is what? Plug it into the calculator, because remember, I want a, not a squared. So what am I referring to? You just got to take a square root of the whole thing. Okay, so let's see what that gives me. So 7 squared, I'm just going to type in 49 plus 11 squared, 121 minus 2 times 7 times 11 times the cosine. Was it 110? Okay. So this is going to give me that diagonal dB. So I'd say 14.9 and then 2 repeating. Okay. So you probably could make an argument to go ahead and say 15, but I'm going to go ahead and do this. I'm going to put 14.9 right there. See, now I've got side angle side. I can apply that to the same formula. Okay. So I can go ahead and say I'm going to take 1/2 of that 14.9 times 16 times the sine of 40. Oh, thank you. Ooh. So now this top one represents the area of triangle ABD. This one that I just wrote, that represents the angle, or excuse me, the area of triangle BCD. So if I want the total area, just got to add them up. So I would actually probably just go ahead and type everything in the calculator. And even though I put 14.9, I'm going to use the actual value in the calculator so that my answer is more approximate. So let's go over here. So 1/2 is 0.5 times 7 times 11 times the sine of 110. See, that right there is just the area of the first triangle. Now I'm going to add it to, that was interesting, plus 0.5 times, well, one side length we just found to be the 14.9 times the other side length 16 times the sine, and what was that angle measure? 40. Okay. So there we go. The area of one triangle plus the area of the second should give me the total area of the figure, which I'm getting to be about 112.9. Okay. So with 0.9, again, you could probably go ahead and make the argument, just say 113. Did it actually tell me how to round? No. So let's say the overall area is about 113. Now we're talking centimeters squared. Okay. I would go 113. I mean, 112.9, really close. Really close. Okay. Did anybody happen to have that done before we talked together? Brandon? Okay. Anybody else? Did anybody else remember that formula? Don't remember that formula? Okay, there you go. All right, good, good, good. Okay, so that is our fourth and final focus activity. Like I said, we'll turn those in later. We'll turn those in later. Okay, so let's see. What do we got now? Okay, let's get back to vectors. Oh, actually, don't need that anymore. Okay. Oh, interesting. All right, so we're about to finish up this first set of notes on vectors, and then I want to go ahead and start showing you some word problems actually using the stuff we've been talking about. So we talked about component form, magnitude, we looked at unit vectors, we finished up yesterday with linear combination. Now remember, linear combination was just a horizontal unit we call I, so that was 1, 0, and then a vertical unit, J, that's just 0, 1. So going back and forth between linear combination and component form is very, very simple. You just use the coefficients. So let's say I have vector u, and the component form is a -7, 1. Okay. Well, what's another way, an equivalent way to write that in linear combination form? Now remember, I want to write this in terms of I and j.
Yeah, so like -7i.
So -7i plus the 1j. There you go. Oh, okay, I got you. Got you. That's all you got to do. It's very, very simple to go back and forth. Okay. Now this right here, if I were to ask you to determine that, what does it mean when I have the double bars? Starts with an M. The mag. That's the magnitude. What was the formula for the magnitude? There you go. Square root a squared plus b squared. And remember the component form, that's a and b. Well, same thing here. The coefficient of I is a, coefficient of j is b. So this would be the square root of -7 squared plus 1 squared. So it looks like I have the square root of 50, 49 plus 1. Now, is this a radical that can be simplified? What's a perfect square that'll evenly divide it? 25, because the square root of 25 is 5, right? So I can rewrite this as 25 times 2. So the square root of 25 is 5, but if I take the square root of 2, I get a decimal. So that would be the magnitude. That's it. Okay. Well, 5 times 10 would give you 50, but you'd have to break the 10 up into 5 times 2 again. So you could, yeah, if you don't want to look it up by perfect squares, you could go ahead and just break it up into a product of prime numbers, and then every pair you pull one out. Like, for example, yeah, I see what he's saying. Like, if you had the square root of 8, you could say that's the square root of 4 times 2. See, 4 is a perfect square, right? But if I broke it down into nothing but prime numbers, with a square root, for every 2 of the same number, I can pull one out. But see, I've only got 1 2 remaining, so he has to stay inside. Oh, yeah, so there's a ton of different ways to simplify those radicals. Good, good. I'm actually glad you remembered that. Okay. Well, I'm going to go ahead and make this the last problem in this set of notes, and then we're going to move over to that other packet. I'm going to kind of forego that last example that we have here because it's pretty different from the other ones I'm going to want you to do, so I'm not going to worry about looking at it. So here we go, the direction angle of a vector. The direction angle of a vector is the angle the vector makes with the positive x-axis, and that's key. It always, always starts rotating from the positive x-axis, standard form. So if a vector v is equal to AB in component form, we know that A is equal to the magnitude of V times cosine theta, B is equal to the magnitude of V sine theta, and we know that tangent of theta equals B divided by A. So it gives you a formula here. Let's say if you want to know the component form of a vector immediately, I want to know that AB combination. If you know the magnitude and the degree measure, this formula you simply plug in and it gives you everything you need. Okay, so let me show you what I mean. These formulas are great, but I would go ahead and write this. The magnitude of V cosine theta, comma, the magnitude of V sine theta. That's the formula you should use. The other versions are here on your notes, but I would say that is the one that we are going to be using probably 100% of the time. Okay? This one is crucial to us when we're solving these word problems. Okay? Now, before we go ahead and get to an example, you might be wondering, why is A equal to that expression? Why is B equal to that expression as well? Well, take a look at the little graph that I have over here. Okay, you remember how we would draw a terminal side? And then I'd go ahead and connect it to the x-axis and make a right triangle? You guys remember that? Okay, well, let's say that the horizontal is A, because remember, that's what we're saying in component form. So A is your horizontal distance. What's the vertical? It's B. Well, does anybody know what the length of that hypotenuse would be? Now, we could call it C, but let's say right now, let's go ahead and put a C there. Okay, let's go ahead and use the Pythagorean theorem. We know that A squared plus B squared is equal to C squared, right? So how would I find C? What would I do to C squared to get C? Square root it, right? That means I'd square root the other side. Does that look familiar to anybody?
Oh, that's that one.
What's that word? Starts with an M? That's the magnitude. Okay, so the hypotenuse would be the magnitude of the two sides, right? So let's go ahead and say the magnitude of V, because this is vector V that we're talking about.
Oh, it makes sense.
Well, let's go ahead with theta given to me. See, we don't know what measure theta is, but I just know it's the reference angle right here. Let's go ahead and create a trig equation for sine and cosine. If I were to say cosine of theta equals, well, what ratio does cosine have? It's what over what? It's always x over r, the adjacent over the hypotenuse, right? Well, here, what's the adjacent? A, B, or the magnitude? A over the hypotenuse, the magnitude. Well, let's say I wanted to solve that equation for A. I'd multiply both sides by the magnitude of V. Because what's going to happen over here? See, those magnitudes cancel. A equals the magnitude times cosine theta. You're going to be able to do the same thing for sine. Now, while cosine is adjacent over the hypotenuse, what's sine? Okay, y over r. Opposite over the hypotenuse, right? Well, what's the opposite for theta? B over the magnitude. So how would I solve that for B? Times the magnitude.
How does that work, though?
Well, remember, the magnitude, that's just a number. And it could represent anything. It could represent the length of the arrow, could be the speed, anything. But it's just a number. Okay? So, like, if I were to have, let me go ahead and give you an actual example.
So it's like 4/3 magnitude.
Yeah, you remember way back when we were first doing trig equations, let's say, this is just what if. Let's say sine theta was 45. So if I'm going to say sine of 45 is equal to, and let's say B over 2. Let's say that the hypotenuse was 2. Well, see, what we're doing here, if I wanted to solve for B, then I would just multiply through by 2.
That's basically all.
Yeah, so see, we're doing the exact same thing, but I'm just using the variables. Okay. So does that make sense now why this is my A, this is the B? Okay. Well, here's why that little formula is going to be so nice to us. It says write vector V as a linear combination of the unit vectors I and j if the magnitude of the vector is 4 and the angle measure is theta equals 30 degrees. See, here's the thing. If you are given the magnitude and theta, we know the magnitude is 4, and I know theta is 30. Here's my formula. The magnitude of V times the cosine theta, magnitude of V times the sine of theta. You simply go ahead and plug in. What was the magnitude again? So I'm going to say 4 times the cosine of what? 30. Comma. Magnitude sine theta would be 4 sine of 30. And then we just go ahead and simplify this. We'd go to the calculator. Okay, so 4 cosine of 30, let's see here. So 4, if it'll type it out for me, there we go. 4 cosine of 30.
So is it gonna be on the unit circle? So like if I went to 120 on the unit circle and I looked at that at night.
Oh yeah, you absolutely could, because 30 is a measure that you're going to recognize on the unit circle. So you could do that. Here I'm just going to go to the calculator because that's what we're going to be doing in our problems. So I would say, let's say 3.5 for the A value. So this is 3.5. In fact, can anybody help me out? What is 4 sine of 30? That is just 2. See, right there, that immediately gives you the component form. Now, the problem said it wants to put it in linear combination. So, could you just give me that in linear combination?
Yeah, just throw an I and a J.
There you go. So what would it be? 3.5i plus 2j. That's it. If you know those two items, that is everything you need for a vector. Okay. How we doing? Are you good? Okay. All right, now like I said, I'm going to go ahead and skip past this guy right here. It's not even similar to the problems you're going to see on your homework. If anybody wants to come back and do it, we will. It's actually a pretty cool physics problem, but this isn't a physics class. Let's take a look at this guy right here. This other packet that I gave you when you walked in. Okay, so this is going to help me out with some of these word problems. We need to know about directions here. The direction of a vector can also be given as a bearing. A quadrant bearing phi is a directional measurement between 0 and 90 east or west of the north-south line. The quadrant bearing of vector v shown is 35 degrees east of south, or is written south 35 degrees east. With a quadrant bearing, you have to have a measure less than 90. The reason we call it a quadrant bearing is because it's limited to one quadrant. The first thing you're going to do is put north or south. It's going to have you decide if you're going to go with the positive or the negative y-axis, and then from there, you rotate left or right. Okay? If it's west, you rotate left. If it's east, you rotate right. So take a look at the example we were given. It says south, 35 degrees east. So I'm going to start at south, but now it says 35 degrees east. So do you think I'm going to rotate left or right? Right. So this little angle right here, this is what we're referring to. That's 35 degrees. Okay. So what if I were to give you a quadrant bearing that said south 50 degrees west? There you go. So see, I'm going to start with south. So I go to the negative y-axis, and because it's west, I'm going to rotate from here. And where I stop, that would be 50 degrees. See, that's a quadrant bearing. Okay. So what if I wanted my vector to be in quadrant 2? Then I'd say north, and what would the other direction have to be? West. But it has to be a measure less than 90. So if I were to say something like, 20 degrees. So because it starts out by saying north, I'm going to start off the positive. And because it says west, I'm going to rotate left. So this would be 20 degrees. It's still positive, yes. Okay, you always rotate left or right off the y-axis, and it always stays positive, yes.
So it's different from
Yes, it's different from what we were talking about on the unit circle. So see, this gives me a specific place, quadrant to go to. So any questions about quadrant bearing?
I have a question.
Can we put a what? Oh.
Yeah, buddy. Wait, no.
See, the nice thing is I'm recording, but nobody can see what I just did. All right.
Wait, why do fraternities and
I know, right?
math things?
I'm sorry, what?
Why do fraternities and sororities have those Greek names? Because they're pretty. Yeah.
You know, I don't know the actual reason why, but they always do use Greek letters to represent their organizations.
Alpha, beta, kappa.
Yeah.
I don't know.
It is pretty cool. Yeah. Okay. Now there is one other type of bearing. A true bearing is a directional measure where the angle is measured clockwise from north. Now that's the trick. You always start with a true bearing. You always go clockwise from north. So that means I'm going to start at true north, and I continue to rotate as far as I need to. That's a true bearing. Remember, a quadrant bearing is going to identify exactly what quadrant I'm going to go into. So for this one right here, when I was talking about south 35 degrees east, if this one was 35 degrees, well then this would also have the exact same measure as a true bearing at 145. Because what's 145 degrees plus 35? 180. See, I just took the difference. Okay. So if I were to go ahead and give you another one, like let's say I gave you a quadrant bearing of, how about south 20 degrees west? What quadrant would that put me in? I heard 3 and I heard 4. It'd be 3, right? So we're going to choose south first. Am I going to rotate left or right? Left, because it's west. So I'm only going to rotate 20 degrees into quadrant 3. Now, this measure right here, south 20 degrees west, is going to be equivalent in true bearing if I start here and rotate all the way around. 180 plus 20, there you go. A true bearing of 200 degrees would have the exact same location as a quadrant bearing of south 20 degrees west. Does that make sense?
So that's it?
That's it. That's all a true bearing is. Now, there's a couple of characteristics of true bearings. They're always given in 3 digits. So a direction that measures 25 degrees clockwise from north would be written as 0, 25 degrees. So it's the little things like that that's going to tell you what kind of bearing you're going to have. If you actually have the given measurements, north, south, east, west, guaranteed it's got to be a quadrant bearing. If it does not, then it's either starting with the horizontal or it's a true bearing. If you see a 0 in front of it, absolutely going to be a true bearing. Okay. So let me go ahead and give you another one. Maybe another easy one. How about if I were to go ahead and say, north 80 degrees west? What quadrant would that put me in? The second. Because I'm going to go north first. So here's north. And I'm going to rotate left or right? Left, because we have west. So I'm going to rotate over 80 degrees. Okay. So what would be the same measure, but only recorded as a true bearing? So I would start here and go all the way around. Now 190. Now think about it. What's 1/4 of the circle? So we have 3 of those, so that's 270. So what would this little angle right here be? So this would be 280. So a true bearing of 280 degrees would have the exact same location as north 80 degrees west. Is that making sense?
Yeah.
Everybody's okay with that?
Oh, okay, I got it. Never mind.
We're good?
Yeah,
Okay. So let's work some examples. Now, this one says use a protractor, all that stuff. We are not going to worry about that. We're just going to go ahead and sketch these. So let's say, first example, we have vector A, 20 feet per second. So the magnitude is speed here at a bearing of 0, 30 degrees. Now, would this be a quadrant bearing or a true bearing? It'd be a true bearing. How do you know that? It's got the 0 in front. So true bearings always start at north and begin to rotate clockwise. So what quadrant would 30 degrees put me in? It'd be the first. So this right here, that would be a True bearing, 30 degrees. True bearing, you always start at north and rotate clockwise. Okay. Now let's try the next one. Vector V, 75 pounds of force. So here the magnitude is force. But it says 140 degrees to the horizontal. Now this one doesn't say bearing. When it says to the horizontal, it's actually telling you to start where? Where did we always start rotating on the unit circle? Standard position. That was the positive x-axis. So if it says with the horizontal, you got to start rotating from standard position. That's how we've been normally doing it. Okay. So if I were to rotate 140 degrees, it's not going to put me in the third. Put me in the second. Because remember, this is 180, so it'd have to be larger than 180 to get me in the third. So this right here, let's say that would be vector V. That's 140 degrees. Excuse me. Okay. Last example. Vector Z is 30 miles per hour. Okay, so again, my magnitude is speed at a bearing of south 60 degrees west. So what kind of bearing is this? Is it true or quadrant? Quadrant bearing, okay. Now, how do we know it's quadrant? Because of the south and the west. If you're given any of those four directions, it's quadrant bearing. So what quadrant would that put me in? Okay, so here's north, south, east, west. Yeah, so I'm going to start at south. Now because it's west, I'm going to rotate right there. So this would be 60 degrees. That's the quadrant bearing. Now let's go ahead and tie all this together. Let's go ahead. What would this same measure be as a true bearing? Would you guys agree? That would be 240 degrees. Yes. Now, one other, what if we started measuring from the horizontal and we came all the way around here? Now, what's the difference, this little angle here? That's 30, right? Because remember, a quadrant's 90. So from the horizontal, this would be 210. So all three of these have different measures, but they're all representing the same vector. Is everybody okay with that? Any questions on quadrant bearing, true bearing, horizontal?
Those things at the beginning don't really matter, right? The 20 feet per second, 75 miles.
No, typically what we would do is, for like these problems here, we just went ahead and did the last one. I would go ahead and put 30 on that vector. Okay. So even though we're talking about speed here, if you think about it as being a length, it really helps when you're doing it graphically. But the one thing I did decide, we're not going to go ahead and be looking at these graphically. If you want me to, we can do that. But I'm going to show you how to do it algebraically. We're just going to choose one method, and we're going to be consistent because I don't want to confuse anybody. Okay. So let's at least start this one problem here, and we'll probably have to finish it up tomorrow. But it says, and you'll notice for the other, my IS classes, I did show them both, so don't worry about the diagram. But it says, in an orienteering competition, Tia walks north 50 degrees east for 120 feet, and then walks 80 feet due east. How far and at what quadrant bearing is Tia from her starting position? All of these problems are going to be done the same way. You're going to be provided two vectors, okay? So one vector is she's walking the 120 feet. Okay, choose a variable for that. Let's say x. So let's say x represents the vector where she's walking north 50 degrees east for 120 feet. Now I need a variable for the other distance. Y. Okay. Now once you've identified those, what you're going to go ahead and do, in order to answer the question, you have to find a vector that we call the resultant. Now the resultant is very easy to find. You take the two vectors that you have and you simply add them up. Okay. Now let's go ahead and figure out how am I going to find x and y. Let's start with x. Now you remember that formula that I said was going to be super important to you? That's where this guy's going to come into play. The only thing about this formula, theta has to start rotating from the positive x-axis, from standard position. So this is the one thing you have to be careful about. Now, maybe looking at it graphically will kind of help out. North 50 degrees east would actually be in quadrant 1, right? It'd actually be this guy right here. So let's say this is 120, but this is 50 degrees, right? So what's this measure right here? If the other measure is 50 degrees. 40. So when I go ahead and plug into the formula, I need to use 40 degrees, not 50 degrees. Okay, we can only take the measure of theta from the x-axis. That formula is very specific about that. So what's her magnitude on vector x? There you go. Remember, magnitude could be anything. It could be the force. It could be speed. Here, it's distance. So she walked 120 feet, and I'm going to say cosine of what? 40. So now I need to go ahead and put magnitude sine of theta. So what's the magnitude? Yeah, it's still 120, right? It's still the same magnitude. So 120 sine of 40. And there we go. Just like we did a moment ago. I'm going to be able to get decimal answers on that. I'm going to have the component form. Okay. Now, let's go ahead and do this one. Y equals. Okay. Now, it says she walked 80 feet due east. So let's think about this. If she's walking due east, okay, well, what's the angle of rotation coming off the x-axis? 0. There you go. There's no angle at all because she's walking in a specific direction. What's the magnitude? 80. So help me fill in this formula for her second travel. Oh, no. Now, what's the magnitude? She walked 80 feet. So 80, what? Cosine of 0, comma, 80, sine of 0. There you go. We're going to be using that formula over and over again. Now, remember, this is the first one we've seen where we have to do this, and it's probably a little unusual. That's okay. Okay, we're going to work some more examples. We're going to take our time. We will get this. Okay. All right, so I'll tell you what, I've got 31. We will just go ahead and pick up there tomorrow. And actually, there's not a lot left in this problem. Okay. There you go. Yeah. So that would just be, yeah, because 80 times 0. You're absolutely right if you're looking at the unit circle. Yes. Yes. Perfect, perfect, perfect. I do want to save changes. I do want to save changes. Woohoo. Oh, sorry. Yes. Mm-hmm.
Russ, if you don't mind, can you look at the rest of the columns a little bit?
Into lunch? No, sorry.
Oh,
I mean, we can, but just not right now.
It's not right now?
Yeah.
Okay.
I
When
get
do
tired
you
of
think you'll have grades entered by if I could really take it tomorrow morning?
Well, everything's entered so far except for the uh, focus activity, but I could easily put that in just to see where you'd be at.
As soon as I like take the exam, like
Mhm.
take it.
Oh yeah.
Okay.
Oh yeah. Well,
I just have some, because like we have this trip going on for ROTC. And
Oh, yeah?
Light is supposed to
okay.
so there's
Gotcha.
pictures.